Hey everyone. So I'm sure your mind is already super full from today, so I'd like to talk to you about nothing. Can we do anything with nothing? And what is nothing, actually? So if I think about nothing, I think about my ideas for new research proposals, or when I'm standing in front of the fridge at 3 a.m. in the morning trying to find something to eat. I also have this very suspicious magician's hat with me, with nothing in it. Or what about the vacuum of space? That's pretty empty, right? There's some obvious things we have to get rid of, so let's do that. But that should be pretty much nothing. Well, as a physicist, I can tell you, even the vacuum is not really empty. There are always so-called quantum vacuum fluctuations present, which we can imagine as pairs of particles and antiparticles being created on very short timescales, which then annihilate each other again immediately. And because it happens so fast, it doesn't really influence our everyday lived physics. But can we do anything with these quantum vacuum fluctuations? Can we, for example, make them real? Or make light out of the nothing? Actually, yes. If we believe what Stephen Hawking proposed in 1975, bringing together the two big theories of physics, gravity and the quantum fields of our standard model. He proposed that black holes exactly do that for us. They create light out of the nothing and radiate so-called Hawking radiation. And because of that, they're actually evaporating. But how can we imagine this is happening? Well, at the edge of a black hole, we also have our quantum vacuum fluctuations. And then instead of annihilating each other again, one part gets sucked into the black hole and the other part can escape as Hawking radiation. So I went up to the DFG and asked if I can have funding to get a rocket to measure this Hawking radiation. Unfortunately, they said no. To be honest, I didn't really ask, so there's probably someone from the DFG in the audience. Do we have money for a small rocket to go to a black hole? No? Okay, that's fine. Instead of going to a black hole, we can bring the extreme environment of a black hole down to Earth. And don't worry, I will not create a black hole on Earth. So first we have to confine and control our quantum vacuum fluctuations. And therefore we put them in between two mirrors, the so-called cavity, where they can bounce back and forth just like light. And actually I have a cavity here as well. And then we can use a trick. We can add some resonant matter into our cavity. And then they will interact with the quantum vacuum fluctuations through something called light-matter coupling. And this is actually strong light-matter coupling, even ultra-strong light-matter coupling. And now this environment for a quantum vacuum fluctuation is so extreme, we can actually significantly increase their number into our cavity. And don't worry, I will not bother you with the quantum mechanics about that. So now, we have these quantum vacuum fluctuations in our cavity. Can we somehow make them real? Well, it's very easy. We just need to pull apart our mirrors. And if we do this fast enough, we can get exactly the same as at the edge of a black hole and make these quantum vacuum fluctuations real photons. And in the lab, this looks a little bit different. We use these gold microresonators instead of our two mirrors. And then we substitute this generic matter cube I have here with a 2D quantum system below that. This is then how a sample looks in real life, and if we zoom in, we can see our gold microresonators. And then we put the sample into this big green cryostat you can see in the front. And because mechanically moving two mirrors apart is still way too slow, we actually use this big laser system you can see in the background to exactly achieve that. And we need to modify our sample a little bit, so we add these semiconductor patches in between our two systems. And then we use a laser and shoot an ultra-short, intense laser pulse onto our sample, which completely destroys the cavity. And then if we measure how fast this actually happens, we can see it happens in about 70 femtoseconds, which is 7 times 10 to the minus 14 seconds, so very short. And let's see if we were actually fast enough. And there we have some vacuum photons. Let's see if it actually works here as well. And yeah, there are some vacuum photons. So Have we proven Hawking right? Are black holes evaporating? Well, as it is with science, we like to have clear-cut answers. But unfortunately, measuring these photons down on Earth is still extremely difficult. So until then, I can at least reassure you that your fridge is never really empty. Thanks.